Okay, so let us recall that in the previous analysis video we discussed many results without proof, mentioning that the proofs will be handled in the exercises. And towards the end of the last video we also discussed something called Riemann's theorem or Riemann's result, which says that if we are given a conditionally convergent series that is not absolutely convergent, then its terms can be rearranged to make it converge to any real number. So ideally today we should look at that result and its proof, because its proof is not an exercise, it's given in the text. But that is something which is the end of the section, and we have seen so many unproved statements in the previous video. So I think it would be better if we first prove those statements and then only we discuss Riemann's theorem. So today we are going to start solving the exercises, and this is the first one. So here we need to prove lemma 823. So let's start by recalling the statement of this lemma, and then we will see how we can prove it. So in lemma 823, I of course I am not going to write the whole statement formally. I will just say what the thing is. So in this lemma, x is an at most countable set, and f is a real valued function with x as its domain, then the sum of the functional values as the variable x varies over x is absolutely convergent. Let me write that in short like this, you will understand. If and only if, which often we write as IFF, you may know this supremum is finite. Supremum of this set of such sums over A, where A is a finite subset of x. This is less than plus infinity. So we need to prove this. But in order to prove this, when we try to prove this, we first encounter a problem. The problem is that x is an at most countable set. So x is not necessarily countable, x may be finite also. And the problem is this: in our first definition, that is in definition 821, which is the first item of this section, we have, what is this definition? This is the definition of convergence, absolute convergence of such sums. In that definition, our set x is countable and not at most countable. So we only know what absolute convergence of such sums means when the set involved is countable, but we really don't know what absolute convergence of such sums means when x is finite. We do not have that definition. So that means we need to first of all extend this definition to include the case when x is finite, because otherwise this statement is in fact meaningless when x is finite. When x is finite, we don't know what absolute convergence even means. So we need to define it first of all. So accordingly, we are going to now start the solution by addressing this issue and resolving it first, and then we will start the solution proper. So let's go like this. Note that in the statement of our lemma, eight to 3, x is at most countable, but in definition 8 to 1, x is countable. So I think we can get rid of this. We can erase this statement now because we already know this and we have seen it once more. We need to prove that this is absolutely convergent if and only if this supremum is less than infinity. And note one more thing. I think I discussed about this before also, but anyway, let me say it once more. You look at the elements in this set. The elements are what? They are real numbers, of course, because they are sums over finite sets. But what type of real number? The sums involve terms that are non-negative real numbers due to the presence of this absolute value function. So that means each such term, each such sum, these are the elements of this set, they are non-negative real numbers. So by the definition of supremum, the supremum is also a non-negative real number. That means this thing is going to be greater than or equal to 0 always, right? So this supremum being less than infinity is equivalent to it being a real number, because the supremum can never be minus infinity. Okay, so let's keep that in mind, and now let's continue. Okay, so what we have written, note that in the statement of that lemma, x is at most countable, but in definition 8 to 1, x is countable. So to make the statement of lemma 8 to 3 meaningful, we extend definition 8 to 1 to include the case, or should I write like this, include the case, or I can write even more directly like this, to include sums over finite sets by defining the sum to be absolutely convergent when x is finite. That means when x is finite, such sums are being defined to be absolutely convergent. That's just it. No extra condition is needed. That is because we know that such finite sums already have a definition, already an existing definition is there, which we have already seen when we were discussing finite series. Okay, so it seems absolutely natural to define that all such sums are absolutely convergent. In fact, there is no question of non-convergence. We already have values for this quantity. Okay, so this is the slight extension of definition 821, which only treats countable sets, but now we have included finite sets as well. So now this slightly extended definition has treats at most countable sets. So now there is no problem with lemma 823, I mean its statement, which still we have to prove, and we will see whether this extension is going to make it true or not. It is, of course, but we have to prove it now. Okay, now we will start the proof. So in the beginning itself, to make things simpler to write, we are going to define the set that is there in that supremum to be S. We are giving it a name. And in fact, we also give the supremum itself a name. Let us call it small s. And the first claim I am going to make without saying anything further in explanation is this. Clearly, the lemma is true when the set is finite. Although I said without any explanation, that means I'm not going to make the explanation a part of the solution, but for the sake of actually explaining this thing to you, I'm going to write an explanation. Why? Why is it clearly true when x is finite? Oh, we are not saying lemma 823, so let me put small n. Okay, so when x is finite, what happens to the sum? We know that it is absolutely convergent by this slight extension of definition 821. It is absolutely convergent. Now what happens to S when x is finite? In that case, S itself is a finite set, 1. Note that since x is finite, its number of subsets is also finite because the power set of x is finite. In fact, we have proved this. When x is a finite set, then its power set is also finite, and we also know what the cardinality of the power set is in that case. The cardinality is this: 2 to the power the cardinality of x. So we know that it is finite. So that means in the set S we have only finitely many sums. So S is a finite set of real numbers. Hence its supremum will just be the maximum element in the set, and which of course naturally is also a real number and hence strictly less than infinity. So in this case the series is also absolutely convergent, and our supremum, that is small s, is also less than infinity, or the same thing, small s is a real number. So that is the explanation of this last line, the previous line. Clearly the lemma is true when x is finite. So now we can consider the case where x is countable. Now let x be countable. Now in this case we need to prove the lemma, and we need to prove two statements, both the directions, which are converses to each other. So let us first assume that our series is absolutely convergent. That means what? Now because x is countable, absolute convergence of this series is just our old definition 8 to 1. So by that definition there exists a bijection say G1. I am taking 1 because we will have to consider another bijection like this, which I will call G2. Such that the series summation absolute value of f of g1 of I as I varies from 0 to infinity is convergent. And this fact is coming directly from definition 8 to 1. Okay. So now what we need is this. We now need to somehow from this thing prove that S is finite, small s is finite. So how are we going to make the connection? So we need to say something about small s, namely that it is a real number or that it is less than infinity. So that means we need to know what capital S is going to be, or rather what its elements will look like, and for that we need to consider any arbitrary finite subset A of X. So this is how we go. For any finite set A which is a subset of X, G1 inverse of A is finite. And hence G1 inverse of A is going to be a subset of T, where T is the set of all natural numbers less than or equal to capital N for some positive integer N. So what have we written here? We are considering an arbitrary finite set A, and we are saying something about G inverse of A, G1 inverse of A, that is the inverse image of A under G1. The first thing we are saying is that this is a finite set. And why is that so? That is because G1 is a bijection. So if you are taking any subset A of X, then you consider its inverse image. Well, not any subset, any finite subset A of X, and consider its inverse image under this bijection, then not only is it going to be finite, a finite subset of N, but it will have the same number of elements as A. Okay, but that is because G1 is a bijection of one-to-one correspondence. So when it's like this. This is your N, this is your X, and you have the bijection G1 here. So this is your subset A. It's a finite subset of X. Now, as you narrow your focus on A only and see what G1 does to A, then G1 takes A to its inverse image under G1, which is a subset of N. And because G1 is a bijection, just like G1 is a one-to-one correspondence between N and X, it also becomes a one-to-one correspondence between A and G1 inverse of A. In other words, if you focus your attention on G1 inverse of A, technically speaking, if you restrict the function G1 on G1 inverse of A, then this restriction itself becomes a bijection from G1 inverse of A onto A. This is a bijection. So naturally, this is also finite, and in fact its cardinality is exactly equal to the cardinality of A. Okay, so that means this is a finite set, a finite subset of N. But if it is a finite subset of N, so the elements in it are natural numbers. Because it is finite, there will be a largest natural number, and that is why there exists some positive integer N for which the set of all natural numbers less than or equal to n will contain this as a subset. You can take this capital N to be the largest element of this G1 inverse of A itself. So then naturally every element of G1 inverse of A will be less than or equal to capital N, because that is the largest element, and as a result this becomes a subset of T. Okay. Now what is the consequence of these things? Then we are going to have to recall one result that we already know from the chapter on sequences and their convergence, and that result is this. So by proposition 638, we are now going to write some inequalities. First we look at this sum. In fact, since we have taken A to be a finite subset of X, and we already know what we chose this A for, to consider this sum, which is an arbitrary element of our set capital S. Now because we have this bijection, so by the properties of such sums over finite sets, you can clearly see that this sum is equal to this sum. If this looks confusing, you go to the properties of sums over finite sets. There you have one property which allows you to replace a sum with an equivalent sum using such a bijection. You go to the properties, you will realize which one among those subdivisions is the one that we are using here. Okay, so now we are going to write an inequality. This is less than or equal to the sum of such f of g1 of I as I varies over t. Why? Note that there are two reasons for this inequality. One of them is, of course, that this is a subset of T. So that means here we have possibly more number of index values I. The other reason is that the terms involved in these sums are all non-negative real numbers. So if it is the case that this set is equal to this, then that means if this set is equal to T, that is also a possibility, no? In that case we have equality, obviously. But if we have more elements in T than we have here in G1 inverse of A, then for those extra indices you are adding extra non-negative real numbers. So those real numbers may have some positive real number among them, or those real numbers, extra real numbers, may all be zero. That is also a possibility, but in any case we will have this inequality. If there is one extra positive, then we will have strict inequality. That is why we are having this one. So far we haven't used proposition 638, but it's coming. Now you can see that T is just the set of all natural numbers less than or equal to n. So this sum is nothing but this finite series. And if you want to be even more rigorous, you go to the properties of finite series and sums over finite sets. There, actually you will be able to justify each step using one of those properties which are there given as subdivisions. So this sum is just simply this finite series. Okay. Now in the next step we will have to use proposition 638. And so now we will recall the proposition also. Let me first write the next step and then I will justify. The next step is this. This thing, this finite series is less than or equal to the sum of the infinite series. And which is less than infinity. So what have we done in this last step? And for this last step we need proposition 638, so we need to recall the statement of this proposition also. What this proposition says is that if you have a sequence of real numbers that is monotone increasing, by that of course we mean this and that is bounded above by some finite real number, that is by some real numbers. All of these things are less than or equal to m. Then this sequence is convergent, that is its limit exists, that is the first thing. That's the same as saying that the sequence is convergent, and the limit is in fact nothing but the supremum of the set of all terms in the sequence, and it is less than or equal to m. That is the statement of proposition 638 basically. So how are we using it here? You see, we are already given that this series is convergent. So series is convergent means, it means actually what? It means that its sequence of partial sums is convergent. That is, this sequence is convergent. This sequence is convergent. Imagine this sequence in place of this sequence. Now, convergence of this sequence means that this is what we should have. But why is this sequence monotone increasing? That is because you look at the terms of the sequence, the terms involved in each such sum, which themselves are individual terms of the sequence. Each term is a sum. The terms involved in each sum are non-negative real numbers. So naturally, in order to get the next partial sum, say you have the the integer m here. To get the next term, the next partial sum, you will have to consider m plus 1. So that can be obtained by putting or adding the absolute value of f of g1 of m plus 1. which is a non-negative real number. So you will have these inequalities for the terms in this sequence. So that is why this is monotone increasing. So that is why the limit of this sequence, which is just the sum of this series, will be greater than or equal to all the terms. Why? Because the limit will be the supremum of all these sums. That is why. So that's why we have written this is less than or equal to this, and this itself is less than infinity, because that's what we assumed. In this part of the proof, we have assumed that our original series is absolutely convergent. That means this series is convergent. So this now tells us what? This is an arbitrary element in capital S, and that element we have proved is less than or equal to a fixed real number, and this is true for all elements of S. So let's write the conclusion accordingly. Thus, every element of S is less than or equal to the sum of our series. Or in other words, this sum, this real number, is an upper bound for the set S. Hence, small s, which is the least upper bound of the supremum of capital S, is less than or equal to the sum of this series. i.e., since the sum itself is a real number, S is a real number. So we have proved that if our original series is absolutely convergent, then that supremum small s, little s, is a real number. It is less than infinity. Now we have to prove the converse. Conversely, let S be a real number, which is the same as saying that S is less than infinity. We now need to prove that this series is convergent. Well, of course, not exactly this series, but we are going to have to consider another bijection, because you see how, do you remember how this G1 came to be? The G1 exists because it was given that this series is convergent, or rather because it is given that the original series, original sum over the set X is absolutely convergent. It's from that assumption we have the fact that G1 exists. Now that is not the case. Now in fact we want to prove that the original series is absolutely convergent. So we no longer have G1. We however have a bijection, and that bijection exists because X is countable. Since X is countable, there exists a bijection G2. So that's why I chose that one as given. And here any bijection will work. So we have chosen an arbitrary bijection G2. Okay. So now this is our assumption that the supremum of that set capital S of all those sums over finite subsets of X is a real number, is less than infinity. So that will mean this. Then this sum f of G2 of I, as I varies from 0 to n, belongs to S. Okay, I should not have started the sentence like this, because this is something we already know, isn't it? So let me instead write, since this belongs to S, we have for all natural numbers. Now what have we written here? You see, if n is a natural number, then this is a finite series. Series of what? A finite series whose terms look like this. Now if you think about it for a moment, is it not one of those sums that we have in the set capital S? Because in capital S, the general element looks like this. Where A is a finite subset of X. Now in place of A, what we have is this. Or let me just write the sum itself. This sum slightly differently. Or I think it will be better if I just write this instead. Yes. Is this sum over this finite set the same as this finite series? It is, because you see, as you vary X over this, what are the elements in this set? The G2 images of the natural numbers less than or equal to n. But those types of X's only we see here, the G2 images of the natural numbers less than or equal to n, that is for I varying from 0 to n. So this is actually nothing but one such sum. So definitely it belongs to S, and small s is the supremum of capital S, so it is after all an upper bound, the least upper bound of course, but it is an upper bound. So all the elements of S are going to be less than or equal to small s. So like that, this is also less than or equal to small s, and this is going to happen for any natural number small n, because no matter how large you choose this small n to be, still we are considering only a sum over finite set. Hence, while proposition, oh I don't have a, anyway 638, I remember it again. This infinite series is convergent. Why? Because its sequence of partial sums has these terms, and all of those terms are less than or equal to s. Also, we have already seen that such a sequence, due to the non-negativity of the terms, such a series due to the non-negativity of the terms, has a sequence of partial sums that is monotone increasing. So what we see here is that that sequence of partial sums is bounded above by small s. So proposition 638 is applicable, and the sequence of partial sums is convergent, making the series convergent. And in fact, the sum of this series will be less than or equal to small s. The statement that I wrote of this proposition, there I mentioned one capital M. No? You think of small s in place of capital M. So we have proved that for in fact any bijection G2 from N onto X, this series is convergent. So by definition 821 of absolute convergence, our original sum is absolutely convergent. So this is absolutely convergent, and that just completes the solution and it completes the proof. So lemma 823 has been proved now. Now we can go to the next one. Let's see another one. This one is also about proving one lemma. Prove lemma 825, and a hint is also given. We are going to follow this hint. The hint is this: first show that the sets are finite. Are finite with cardinality at most mn for every positive integer n, and where m is just the supremum of the set that we have in definition 8 to 1. Well, not in definition 8 to 1, but in definition 8 to 4. So the first thing we have to do is we need to recall the statement of this lemma. So let us do the recalling part here. So lemma 8 to 5 just says this. Here X is any set. Now X is any set, not at most countable or anything like that. Possibly uncountable. And f of course is a function, a real valued function defined on X, that is a real valued function with X as its domain, for which this series or this sum is absolutely convergent. These are the things that are given. Then what is the claim? I mean, what does the lemma say? The lemma says that the set of those points or those elements in X at which f does not vanish is at most countable. In fact, we need this lemma in order to define the sum of such a series or the value of such a sum when X is an arbitrary set. Because you remember, we encountered this problem. We defined what absolute convergence of such a general sum is, no matter what the set X is, whether finite or countable or uncountable, using the previous lemma that we proved just now, that is that characterization of absolute convergence using that supremum. But then we encountered the problem of what can we possibly, I mean, what value can we assign to such a sum? And in order to see what can be done, we came up with this lemma. I mean, the author mentioned this lemma, and this allowed us to then define the value of this sum as the value of the sum, where we still have the f values, but in place of X we then have this. and due to this set being at most countable, it then falls under that category of sums where it's a sum over an at most countable set, for which we have a definition for its value. So now we need to prove this. So let's see, and now let us see what the hint says. The hint asks us to first show that these sets for each positive integer in this set is finite, and then we have to also show that its cardinality is at most mn, where m is the supremum of this set. So let's see the solution. Now in the solution we are just going to blindly follow the hint. So we write like this: let m be as given in the hint. We need to at least write this much, because otherwise truly speaking, m will have no meaning. You need to say at least that you are following the hint. That's because you may choose to not follow the hint also. We have done this a few times. So here m is what is given in the hint. So that means m is the supremum of this. Now note that because x is any set, this is absolutely convergent, and its absolute convergence comes from definition 824. That means the general definition of absolute convergence, not the first one. So that means what? That means this supremum is finite, that is m is finite. So we write our hypothesis. Our hypothesis means what? Since we are going to prove this lemma, that means the hypothesis we are given here is our hypothesis. So our hypothesis that this is absolutely convergent simply means that capital M is finite, that is, it's a real number. Now the first thing we need to prove is that these sets are finite. Consider the sets, let's give them some name. Bn where n is a positive integer. This is a perfect statement which says that n is a positive integer. This also sometimes is used to mean the same thing, although it's really not strictly saying that. Only this inequality may mean that n is a real number greater than or equal to 1. But in the context we understand n is a positive integer. We need to prove that Bn is finite for each n. Suppose Bn is infinite for some n, some positive integer n, and now we are hoping for a contradiction. Since we can find a finite set A which is a subset of Bn of any cardinality. I should perhaps write any finite cardinality. And to see why, see the solution to exercise 811. Because of this fact, we can choose such a set A with this cardinality. Okay, what is it that we said here? So our supposition is that Bn is infinite, and due to this infiniteness, what we are saying is that we can choose a finite subset of Bn, perhaps, I have already mentioned it here, okay, a finite subset A of Bn of any finite cardinality. That means if you give me any natural number, then I can choose one subset of Bn whose cardinality is that natural number. This fact sounds plausible, but in fact we have actually proved it in the solution to exercise 811. You go back to that solution, you will realize why. We proved this there actually, rigorously. So now we are just going to use this fact to choose a subset of Bn, a finite subset A, whose cardinality is this number. Now let's look at this number for a moment. We see the greatest integer function here, which we have applied on m. What is m? M is the supremum of that set, right? And the elements in that set are what? They are finite sums, that is sums over finite subsets. And in those sums, the terms involved are all non-negative real numbers due to absolute values. So each such sum is a non-negative real number, and because of which capital M is also a non-negative real number. And that is why its integer value, or the greatest integer less than or equal to m, cannot be negative. The least value is that it will be 0. So that means because we have added 1 to it, so this part, greatest integer value of m plus 1, this is a positive integer, and n already is a positive integer, so this product is a positive integer. So it makes sense to say that we are choosing a set A of this cardinality, because had this been negative, then this would be meaningless. Now what can we say about this specific set A? Then you look at this. M is strictly less than this, it comes from the uh, inequalities that we have for this function, greatest integer function. And the other inequality that comes on that side is that m is greater than or equal to the greatest integer value of m. But if you add 1, then it shoots m and it is always greater than m. Okay, now we can multiply and divide by n. And this is the cardinality of A. Okay, now because A is a subset of Bn, so each element in A is what? Is also an element in Bn, but in Bn we have those elements, those x inputs for the function f, where the absolute value of that functional value is strictly greater than 1 over n. So that means if we consider this sum as x varies over A, then because A is a subset of Bn, these inequalities are true for all these x. That means all these absolute values are strictly greater than 1 over n. How many terms are there in this sum? As many terms as we have elements in A. That is, we are going to encounter these inequalities. How many of them? The cardinality of A, that many of them. So naturally this is going to be greater than this. That is, we are adding up all such inequalities to get this one. But this is what? After all, A is a subset of Bn, and Bn itself is also a subset of x. So A is a subset of x and a finite subset. Keep that in mind, because we have chosen it to be finite. So this is one element in that set, capital S, if we want to call it capital S, whose supremum is capital M. So all these elements are going to be less than or equal to M. So we have ended up proving that M is strictly less than M. This is a contradiction. This is an absurdity. And proves that the last supposition is wrong, i.e., what was our last supposition? Namely that Bn is infinite. So it cannot be infinite, it has to be finite. In fact, truly speaking, our last supposition was that Bn is infinite for some n, and that supposition is false. So that means Bn has to be finite for every n. For all positive integers n. Next, we have to prove that the cardinality of Bn. Now that we have proved that Bn is finite for all n, its cardinality is going to be a natural number. Now we need to prove that its cardinality is at most capital M times small n. Say it is not. Next, suppose the cardinality of Bn is at most means less than or equal to Mn. Let's suppose that it is strictly greater than Mn for some n. Then we can go through a similar argument and we will obtain a similar contradiction like this. Then you start with M again, but this time you straight away multiply and divide by n. So this is the cardinality of Bn divided by n. Now again you see the elements in Bn. Now we are not even considering a subset of Bn but the entire set Bn itself, and in Bn whatever x, the elements x we have, for them the absolute value of f of x is again strictly greater than 1 over n. So this is the number of such x's that we have in Bn. So this thing is strictly less than x belongs to Bn, but this is a Bn now is a finite subset of capital X. So this will be less than or equal to M again, because capital M by definition is the supremum of all such sums over finite set. A contradiction again. So the last supposition is wrong, i.e. this must be less than or equal to Mn for all positive integers n. Right. We now claim, the next thing we claim, that the set Y, which is in fact the set about which this whole result is, that is the set of those elements in X where f does not vanish, is equal to, the claim is this, is equal to the union of all the Bn's. Okay, so what, let's once more write what the set Bn is. This is Bn, no? So is it possible that for any element x in Bn, f of x is equal to 0? Definitely that is not possible, because if that is the case, then this inequality will be violated. So for every x in Bn, f of x is not equal to 0. In other words, each Bn is a subset of y. So their union is also naturally a subset of y. Clearly, the union is a subset of y. Now we prove that the reverse inclusion is also true. So let y belong to y. That means what? F of y will be non-zero. So the absolute value of f of y is going to be a positive real number. And so this will be strictly greater than 1 over m for some positive integer m. Usually we justify this by saying that we can choose a positive integer m large enough so that 1 over m is smaller than this positive real number. But what is a more rigorous way of justifying this? It is that this limit is 0. We already know this fact. That is why we have this thing. But then y just simply belongs to Bm, and so y belongs to the union of all the Bn. Thus, capital Y is also a subset of the union of all the Bn's. So you have this inclusion and its reverse inclusion, so Y is equal to the union of Bn. Hence, the claim I think I forgot to write the full hint. No? The hint also says that besides showing these things, I mean that each Bn is a finite set having cardinality at most Mn, we also have to use exercise 819. From this claim and exercise 819, it follows that Y is at most countable, and that's what we had to prove. Now finally, let us note some things about this final part of the solution. How is it that y is countable? How is it following from this claim that y is equal to this? We have already proved that each Bn is finite and this is a countable union of finite sets, which is at most countable, and that's where exercise 819 comes into play, because it is here that we prove that such a union is at most countable. But why at most countable? Will this not be countable? This may not be countable because you see, we have just proved that each Bn is finite, not necessarily non-empty. Some of them may be empty also, and you may actually end up having a union that gives you a finite set. But in any case, y is at most countable, and that's what we wanted to prove. So that's what we have, and we have completed the solution. So with this, let me end the video here itself. And tomorrow we are going to see the field theory video that I failed to upload for some reason last Friday. So see you tomorrow with field theory. We are going to start a new section which shows us how field theory and its results can be applied to answer some questions about constructions in plain Euclidean geometry. So until that, this is me, Lucifer, from A Mathematical Room. Have a nice night.